Good afternoon, everyone. Welcome to the session. So, this is more of the way I planned it is it's going to be more interactive, right? So, I want to know your response and how you are thinking, and then slowly we are going to build the topic, right, as we go about, right? So, I have not come with any slides. I know the rough trajectory that we are going to take, but together as a class, we are going to explore and then go step by step, right? So what we will be looking at is, so this is a topic in the bigger scheme of things, right? So we also have to understand it, since this being an introductory course, and this is like where we have the face-to-face interaction. Do we have a question there? Okay, yeah, sure. Yeah. So I thought that, okay, we will spend a lot of time in understanding why we are doing things the way we are doing, right? So we want to build some, from bottom up, we want to build some intuition and rational and logic to what we are doing, okay? So while this is introduction to reinforcement learning, we will also be looking at the larger question of, okay, in machine learning, where in machine learning does reinforcement learning, I am going to call this as RL, right? RL fit, right? So that's what we are going to first understand, right? That's something that would be one of the goals of this session, is to understand in the overall scheme of things where reinforcement learning in machine learning, where is it sitting? Let's think of this as an anatomy class or something, right? So suppose I'm going to lecture on heart, right? It's just one way of doing it is to just talk about the heart, but then the other way of saying is that, okay, this is where it is placed and this is how it is connected to other parts of the body, so that you get a whole picture of where this subject itself is sitting, right? So where in machine learning is, so our goals, right? So our goals for this session is to understand where in machine learning RL is fitting, right? But then once you utter the word machine learning, then you also have to say, okay, how do we, right, connect, say, AI artificial intelligence and machine learning. These are very simple statements, but then once you understand the import of these statements, right? The overall picture is more complete, and you will be able to appreciate why we are doing the things the way we are doing. Okay, so then we have to figure out how these two words connect, right? And I am going to offer my perspective, each person has their own perspective, right? Then of course we keep hearing other words, right? Such as you have unsupervised learning. So we have to say goal is to say what is RL and how does it to connect to the other keywords. How does it connect to these things, right? Then we also know that we have what is known as unsupervised learning, then we have what is known as supervised learning, then we have what is known as deep learning, then we have what is known as representation learning, right? I'm just putting all these things out in the open, okay? And then slowly what we will do is these are like the jigsaws, right? Then we want to put all the jigsaws together to complete the picture, right? So that is what we will do, and then as we do, we will kind of learn more about reinforcement learning itself, right? Of course, you will have a full-fledged course on reinforcement learning. This session is not about trying to give a crash course, right? What is going to be taught over a course, I will not be able to do it in 2 hours. So that will not be the aim of this session. But the aim of this session is going to, for you to be able to walk out with a larger picture, right? So first let us take a lot of things that are common, right? So then we also have this word, right, which is basically data science, right? So the words like data science, artificial intelligence, machine learning, these are much more general in nature, right? And reinforcement learning is a specific topic, that much all of us can understand, right? But why are we using these words? What do we mean by them? And in what context are these coming up naturally? That's what we will slowly go into, right? First, what we will take up is, out of this, we are going to take up 2 keywords, okay, which is basically artificial intelligence I think I need a bigger brush. Yeah. This is one keyword that you would want to take. Then we would want to look at the keyword learning. Okay. For now, this is our sub goal. The overall goal is the stated goal. We want to understand what is reinforcement learning and how is it connecting to all these keywords: supervised learning, unsupervised learning, deep learning, representation learning, and then data science, so on and so forth, right? But then what we want to do is to first look at what do we mean by artificial intelligence and why are we talking about learning in this context, right? Okay. So first question is that we will take up to answer. I think from now on the session is going to become slightly more interactive. Okay, so you might want to have a pen and paper. Maybe you would want to write down certain things as and when I ask, and then maybe you can respond. Okay. So the first question that we want to ask ourselves is, what is artificial intelligence? Okay. Now again we can break this word down, right? So now all that we are doing is there is no math yet, right? We are just doing a very common sense or a very English way of looking at things. So now what we want to do is, so the moment when I say artificial intelligence, then the natural part that we have to understand is, in order to understand artificial intelligence, we first should be able to understand what is intelligence. Okay. So what I'm going to do now is to play a video. Okay. So now look at the video. Okay, and then some set of videos. Okay. By looking at the video, I just want you to write down what all aspects of intelligent behavior that you saw in the video, and then maybe I want you to give those keywords to me. So I'm going to populate those words, right? Some definitions. This is what we would want to come up with. So just watch this video, and then I want you to come up with a definition of intelligence. I want you to take a couple of minutes, think about what happened here, and then if I ask you to write a definition of intelligence, right? What is the definition that you would give for intelligence? Right? So once we go through some of the responses, we will get some keywords, right? And then we see whether we can put together a definition for intelligence. Maybe now we can sort of pass the mic and then we can get the responses. So meanwhile, what I will do is I will start writing down the responses. Okay. Here. Yeah. He was the first to raise, so.
So intelligence may be defined as the ability to understand the environment, comprehend the context of that environment, and then systematically approach a problem, and then solve it using a method that can be repeated.
It can be?
Repeated.
Okay. Okay. Some more definitions. Couple more we will anyway have chances. I am going to play some more videos. Okay.
Here the intelligence is great, I would say, is solving novel problems using previous learnings or experiences.
Okay. Okay, some more definition.
My definition of intelligence is it's an ability of observing and analyzing the situation and responding to it according to that situation.
Okay. And response, okay. Some more, maybe some definitions in the back.
My definition is
You can be seated, it's okay.
it's just critical thinking, how we think about any problem and act it and solve it.
Okay.
In different methods.
Okay.
How we approach the problem, how we think about it, and make some new ideas.
Okay. Maybe some definitions from the back. Everybody in the back is kind of, yeah.
So, efficiently utilizing the available resources for some tasks.
Resources to,
Achieve the task.
okay. Okay. Some other definition. Can,
Recognizing the patterns and trying to solve that problem using like already patterns.
Okay, pattern recognition is one aspect. Yeah, maybe some here. Three. Okay, maybe there. Okay, one more.
First, it needs to identify the purpose. That is, the main purpose is to pick up the food.
On.
So, from that purpose, it needs to understand activities
Huh?
and properly utilize the available resources.
Okay.
So, first is the purpose, then understand the environment, then effective utilization of the resources available there.
Okay. So if you have very similar definitions, then maybe you can, if you have a slightly different definition, maybe we can, okay, some more. Okay, maybe two more. Otherwise, this will just become a class of definitions. Yeah. Please be seated. Please sit down. Yeah.
Professor Howard Gardner of Harvard University put forth the definition of intelligence, where he says that intelligence is actually multiple, meaning that logical mathematical is one kind of intelligence,
Okay.
but there is musical intelligence, there is body kind of intelligence,
Huh.
ability to imagine the dimensions and so on.
Yeah,
So
sure.
he said that intelligence is multidimensional. It cannot be put down to a single.
No. So, okay. The question was, what do you think is intelligent here?
Well,
I'm not trying to, say that, I'm not trying to negate whatever the Harvard professor says, right? Just thinking, looking at this video, what is your reaction? I'm asking you to react for this video.
well, it is in the context of the video, it is the ability to solve that puzzle.
Okay.
So logical.
Okay. I think some more keywords are to be obtained. So what I'm going to do is, yeah, okay, maybe one here and one here.
Sir,
Yeah, no, you go ahead.
it's like using environmental factors based on previous experiences, based on reward to complete the process. Because like rewards and outcomes are important to find what we will do. Because like if it's a bad experience, we won't do it. Rewards are important.
Okay, maybe here and then here and here. Okay. Let us do this for some time, then.
I think it's learning through failure. What
Okay.
we say is that failure and trying to basically overcome that again through reinforcement, like repeated action. You are trying to basically make your actions right.
I will say trial and error. Okay. Here, then here.
I
think this definition would cover almost all the keywords written in the word. I think the intelligence is the ability to come up with rules to efficiently solve a problem based on a certain given set of data.
Okay. Yeah, here and then there. And then the yellow. No, here, black. Next is the next.
I think the ability to think for longer goals instead of being attracted by the smaller term goals, like learning machine learning to become a data scientist or instead of metrics.
Okay, long-term goal. Okay.
Instead of being attracted by the short-term goals.
Here, yeah.
Intelligence means doing different steps in particular. Either trying other alternatives having some feedback in this.
Other?
Some feedback in this. I have some feedback in this.
Feedback. Okay. There. L.
I think that it's just having the inherent understanding of something. Like you may keep learning from previous experiences, but in the end you know really supposed to have it coded out in your head or something.
How to?
You can learn from previous experiences, but you shouldn't have it hard coded into your brain. How to solve it.
Okay, not hard coded. Okay. Maybe only one more. Yeah. Okay. Maybe two. Okay.
So it's repeatedly understanding the environment and learning from it and achieving outcomes.
Okay. Maybe here. Lot of taxing work. It's okay.
It is the ability to connect things together and come up with meaningful results or like if you have like 340 equations of code, intelligence means to be able to connect it together and come up with a meaning of it.
Okay, only one last.
So intelligence is about adapting to situations in front of you and understanding the consequences of your actions.
Adapting. Okay, so now what we will do is we will try to make a framework, right? So this is all nice, right? So I think certain things slightly that were missing. Okay, let me try and see whether I can get it out from this example. Right, so a simple problem. Let us say you want to catch a train or a flight, right, at 9. Let us say for simplicity train. Okay, 9 p.m. you want to catch the train, and then it takes 10 minutes for you to walk from the front or the of railway station to the platform, right? And say it takes 1 hour from your house to reach the railway station. So when do you leave your house so that you will catch the train? It takes 7? How did you arrive at that answer? Right. But how did you calculate? Right. So you are calculating from, no, you are calculating from the goal, right? You are calculating from backwards. If I have to be there at 9, then it takes 10 minutes. Then you say that, oh, 8:50 I have to be there in the, at least I should reach the front portion of the railway station so that I take the 10 minutes to walk. Then you are calculating from there, right? So you didn't do forward calculation. You didn't say, oh, 6 o'clock, let me try this answer. Oh, maybe 6 to 7, 7 to 7:10, okay, maybe I will reach. That's not how you are doing. Sometimes what you have to do is you have to calculate from where you want to go, then you have to calculate backwards, right? That's also a this thing. Okay, so now what I will do is I will play another video. Okay, so and then again I want you to sort of look at it and then come up with some keywords. Then with that we will be able to again formalize and then go forward. Okay. So again I want you to let me know what different you are seeing, right? We don't want to keep repeating the same keywords. All these things are already present.
Sir, a keyword would be the application of foresight and leveraging intuition.
Foresight, right?
And intuition.
And?
Intuition.
Okay. But actually if you carefully look what the person was doing.
Choosing the best possible way
Oh.
to requirement. Choosing the best possible way to meet his requirement.
Okay. Choose best amongst foresight and okay.
Freedom says optimization.
Okay.
So adapting to the least method with the least resistance.
Method?
Adapting to a method with the least resistance.
Least resistance, okay.
The ability to think parallelly about multiple options and multiple possibilities.
Where is the voice coming from? Such a large class. Okay. Ability to compare?
Compare multiple possibilities and thinking about those multiple possibilities in parallel and choosing the best one.
Okay. So I think maybe we will have one more, okay, only one more definition.
It's to choose the path that improves your performance.
Uh-huh.
So it's not just reaching the objective function, but also such that your performance is improved.
Okay. This again least resistance, choose the best amongst. Okay. So I am going to show another video. Okay. And then that would be the last of the videos. And then again I want to, I am not going to write down anything, but I want you to make a critical observation. Right. So the question is more to do with what is it that you are seeing here? Of course, it's going to do certain intelligent things, right? So how many of you know that octopi, they are capable of solving puzzles, right? They can solve a lot of problems, and they can even solve mazes and so on and so forth, right? Okay, let us first see this come out of okay. So this is this. Okay, let me again play another video. Okay. So, what is the question? So, in order to be intelligent, do you need a brain? How many of you think yes? How many of you think no? Huh? Yes? Whichever definition. Either definition. I mean, how many of you think that in order to be intelligent, you have to be, you should have a brain? Huh?
I think we should have.
Okay. That was a no-brainer. Anyway. Okay. Anyone who thinks you don't need a brain?
I think a person having a brain tumor can't think anymore. So
Okay.
if you want to be intelligent, the most basic requirement is you must have brain.
Okay. So does it have to look like a human brain? Because octopus, I don't think has a brain like we do, right?
So we need a break to explore different possibilities. Just come outside the problem and see a big picture.
Okay, so there is this is a leading question. Okay, the reason why I'm asking this question is, okay, so how are we? So should we not? Okay, so is there anyone who feels that the brain is not a requirement? Okay, let us hear the answer for why brain is not a requirement.
I don't think because when we consider intelligence, it does not involve the knowledge. Like we see every possible animals or the organism is living its own way on the planet. Like these are doing their form of flexibility. It is also important. It's about the term intelligence, how we define it. It's not only means to just know or acknowledge it among the humans. It's mainly every organism doing their own way, living their own.
No, everything has a nervous system, right? No, the question is, do you need a brain? No, so any organism that you mention has one form of the brain or the other, right?
Yeah, in that sense, it's need the brain. It need a physical brain. Yeah.
So any answer which says we don't require a brain, and why? Okay, so many answers who say we don't require a brain.
One example would be algae, as blue-green algae which form structures and also for each food and so on.
Okay.
They do not have a brain but are able to solve problems, and also amoeba displays intelligent behavior, is able to solve problems in its environment, does not have a brain or a nervous system.
Okay.
So it displays intelligent behavior. So
Correct. But then ultimately when we are trying to build artificial intelligence, right, we are building systems like Google Duplex. How many of you know about Google Duplex? So it can converse with human beings. It's able to do self-driving car, right? We are not going to build systems which is going to do survive in the environment that the algae is trying to solve, right? We are still trying to, when we talk about AI, we are still trying to solve set of problems that we as human beings are able to solve, right?
yes, so the environment determines the kind.
So the environment is our environment only.
Yes.
So the question is,
We now have our computers which are made from slime molds, and slime molds are also problem solving in a similar way. So what happens there is they create a different
ChatGPT etc. is not from those things, right?
Yes.
ChatGPT is still something that's useful, right? See, ultimately what I am trying to slowly come to, we will come to that question, is that we are going to talk about engineering things, right? Ultimately, all of AI is going to be engineering, right? Engineering means you should have some principles, right? Some set of formulations and principles through which you go step by step and then you can do something, right? So, the question is that we are talking about human kind of tasks, right? That's why we are building computers so that they can substitute us in some of the intelligent tasks, right? Like playing chess, right? So, in that context, do we want a brain or not? So that's the first question. Do you think we want a brain? Okay. So now whose answer is no? Okay, there is one answer which is no. Okay, couple of, I think already one answer already you gave. So yeah. You gave an answer, right, for this question. Okay, chance to one more person. Okay. Huh? Yeah. Why?
Sir, it may be physical brain fat or dead or low, sorry. You said they have to have some sensors to get the data, analyze the data, process the data, and take actions accordingly. If it is a physical brain, maybe human being can react, can call it zero.
It may be what? That's what I'm saying. So, okay, without the brain, do you think AI is going to happen or not?
It doesn't depend upon brain. It depends upon the processing of the data, taking the data, analyzing the data, and acting accordingly.
Okay, okay, we are getting somewhere. Maybe only one more answer, maybe here. Then, see, part of the exercise is also to keep all of us awake in the afternoon. Okay.
Yeah, so the earlier colleague also told a correct thing that the senses are some way responsible, but there are some reflexes also that are coming from the spinal cord. For example, if you touch a hot body and
Correct.
it suddenly reflexes, so that doesn't require any intelligence. Okay? But the body knows that these things are to be avoided and reflexes automatically. So the intelligence comes not from the brain, but from the sensory organs and the quick reaction that is coming from.
So, if I build sensors, right? If I build sensors, then will I get intelligence?
Yeah, you can get the results.
Oh, we have light sensors, we have camera, we have, so those are the sensors, right?
Yes.
Camera, we have microphone to pick up the audio. Does it mean that you have a conversational AI just by building a microphone and just by building a camera? Do you have a car that can drive itself? So let us say I put LiDAR and then I have a camera, very high resolution camera, and then say I put LiDAR all around the car. It does not give you a self-driving car, right? So it's basically not about the sensors.
Yeah, but you need a storage to keep all that things remembered.
Okay, suppose you store the data. Okay, I have hard drive.
Cerebrum part and that for that you need a
I have hard drive. I will store the data. Then
yeah, then you can have a model that is based in the hard drive that will take all the reflexive action that is pre-trained from the previous actions, then it is stored there. But,
okay, I mean that we have to specify how that's happening, right?
yes.
Okay. See, okay, maybe I think I will sort of go forward with the framework and also maybe highlight why you would need a learning paradigm, right? And also sort of underscore the requirement of or underscore why you really don't need explicitly a brain. Okay. So next exercise is to look at okay. So the first statement that I would want to make is that in order to look at the tasks, right? So task is one of the what? So suppose we want to solve a task, right? So what we want to know is the process of decision making, right? That's what we want, right? So there are so many places we have decisions, right? Actions. This is what we would want to learn, right? This is what we want to know. Ultimately, intelligence is to make decision. So what we want to understand is how decisions are made, right? Because we are never going to reverse engineer the brain, okay? So the reason why I put sort of brain in the center stage for like the past 10 minutes is that every now and then we sort of read some article saying that, oh, AI has done this, data science has achieved this, or machine learning has achieved this, so on and so forth. We want to see that, oh, is it really thinking? Okay? I mean, that question is not, it's not the right way to look at things, right? So you cannot say, oh, does it have a feeling, right? Like, does it really think? Is it really having some intuition, right? Those are things which are kind of not defined very well, right? So would you say that, oh, if I have a car, right? If there is a horse, right? Or if there is a human being, say somebody like Usain Bolt or a horse which is running, you are running because there is an adrenaline high or something, right? So any athlete who is running a 100-meter race is driven by adrenaline, right? So you cannot say, oh, this car is powered, so does it have adrenaline, right? You cannot ask that question. It is that senseless to ask, oh, does it really have a feeling? Does it really have a brain? Can it really think? Can it really have intuition? So these are words that are outside the realm of engineering. Ultimately, what we are doing is, we are going to crunch numbers. We are going to have computers, we are going to crunch numbers, We are going to go through a sequence of operations, and then we are going to spit out an answer, right? So it's all lot of math and computer science all along that has led to us to the current current status quo of where we are with respect in AI, right? Be it ChatGPT, be it self-driving car. This is all engineered systems. Okay, these are all engineered systems which have sound engineering principles which are repeatable. Okay, so now that's what we would want to first understand. We should first understand this. All of artificial intelligence or machine learning has nothing to do with brain or neuroscience or like, does it think like a human being? It might be okay to talk in those terms when it comes to science fiction or when you write popular science. To get motivated, it's okay to talk in those terms, right? But as people of in the business of building these systems, we are as good as we are like mechanical engineers is to building cars or rockets. We are just going to build these systems which are going to take in data, crunch, do some mathematical operations, do some computations, addition, subtraction, right, multiplication and some nonlinear operations, and then we are going to throw out the answer, right? So we should always make this distinction that it has nothing to do with brain, it has everything to do with decision making and how do you formalize this decision making. Okay. So now I am going to ask only one extra question. Okay. So where does this concept of learning come from? Okay, this is something that we should also understand, right? So why do you want learning? Okay, so if I am going to ask you, does IRCTC booking, right, would you call it an AI system? Why? Would you call tax calculation AI system? Why? Maybe one response. Yeah, here. Blue color. That person. Yeah. So the next question is, yeah.
Hello.
So this for these two operations, it's a fixed problem or solution. It doesn't vary, it doesn't change. Because the calculation is only one outcome. It's not predictive or it is not something that is possible.
Okay. Right? Yeah. So, okay, I am going to ask you another question, right? So, what distinguishes a calculator from a computer? Suppose I break up a computer and I break up a calculator, right? Physically, if I examine, both of them are made out of electronic components, right? So, what is that differentiates a calculator from a computer?
So calculators are specifically programmed to perform mathematical operations, whereas computers are more general, they can perform a variety of operations. Calculators are used for performing solving mathematical problems. So
Okay.
their scope is limited to that. They cannot.
Okay. Slightly better answer. We can improve the answer. I will give a calculator with a lot of memory. Does it become a computer?
So both calculators and computers can do similar mathematical operations. These operations in computer can be made into a more complex program which can perform other tasks.
So basically, programming is the one that differentiates a calculator from a computer, not memory, right? So what differentiates AI from just a program? Huh? IRCTC also interacts with you.
Performs only fixed calculation, but AI interacts in a different way. The changes will affect over there.
Okay, so now let me ask you another question. How would you go about programming IRCTC, let us say?
I just book a ticket over there.
No, if you have to write a program. Now, I am just trying to get at a much more fundamental problem here. Okay, one there. Yeah. Some people from the back, people from the front have had enough chance.
something like a simple computer program is like hard-coded, where if I click this, do this, if there's this many seats, do this. Whereas artificial intelligence would be where the program changes itself or makes its own decisions based on how it's trained and what's happening, what rewards it's getting, and it changes its own program based on that. Or it changes what it does.
Okay, that's a slightly better improvisation. One more. Already you got chance. Same question. Okay, let us give chance to some people.
I think it's different from the, as Mr. IRCTC is only based on the calculating way. Like if there is still difference only, so like whether it is confirm or either no.
Okay.
But whereas the artificial intelligence involved, it mainly involves the intelligence, which means it will show the every possible way of the results, including the intelligence based on the data available, resource available, and everything is controlled. Not only the other data like yes or no. It will show the every possibility.
Okay.
I can't say.
Okay, he is dying to give an answer. Okay. Okay. No, yeah, let us give it to him. Okay, you can answer, then you can answer.
Regarding AI or artificial intelligence, we need to have some prior experiences to make it learn something. But when programming, we don't need to have prior experiences. Like we can just put in the formula and we follow that strict formula by itself.
Where is the formula coming from? That's also coming from prior experience, right?
Not really prior experience, the solutions or anything.
Without knowing how IRCTC works, you wouldn't have been able to program, right? You still need some information, prior information.
But no prior experience regarding the output we need, right? Yes.
Okay. Maybe there. Yeah.
AI can change its response depending on the situation. AI can change its response depending on the situation.
This also can change the response, right? Like depending on you say 2 tickets, it will do 1 response. If you ask for, from this station to this station, there also response changes. Yeah. Okay, so okay, only one answer. You can, yeah.
Programming results in an absolute correct or wrong result. Whereas AI would result in the least wrong result. Basically, it comprehends context. So,
okay.
So that's why.
Why is it not a program? What is so different from a program? So if I take sorting and then somehow give, I take a program and then make it slightly, does it become AI?
No, sir. Basically, AI has the understanding of the context of the problem.
Okay. IRCTC does not understand for whom the ticket is being reserved or from which station to which station. That's the context here, right? It also understands, right? If you're asking from Mumbai to Delhi, then it understands that it is a Mumbai to Delhi ticket. It's not going to give a Chennai to Mumbai ticket, right?
No, but an AI program would be able to cater to your needs better because it will understand if you have to urgently travel or if you have to be there.
Okay, this is all okay, good. So it has no mind to understand. There is no magical ability other than what you would code up. Okay, so that's exactly why I am trying to ask this question. That's not the differentiator, right? Maybe here, then here. So many people, and then we have to go to the next.
Without any human intervention, if you do the work, that means IRCTC, we are using the human being.
Without knowing, it reads your mind and then directly sends. That is AI.
I think if I want to book from here to Chennai, here to Mumbai, just tell I want to book the ticket. Then without my intervention, by using my speech only, it will book and.
That is speech recognition. So what you are saying is speech recognition. That's not okay. I am going to ask you another question. Everybody knows to walk? Okay, only one more answer. Here. No, already, okay. One more.
So I think why IRCTC is not AI-based is because we are not into this learning yet. Because AI is basically a black box, right? Because if we input some data and expect the parameters, we support some data, set the parameters, and AI will generate an answer, but we are not sure what's going inside the AI.
So if for AI to happen, it should be a black box. Is that what you are saying?
Yeah,
Yeah, because the conventional networks, we are not at the current state.
Okay, fine. Okay. There, maybe there.
Sir, I think that in AI you teach the program to think how a human think, like teach the program to think how a human brain thinks. So like in the IITTC program, for focus kind of limited. Whereas in artificial intelligence, you like if you change the inputs, like then the output also changes.
Everywhere if you change input, output changes. Okay. Okay, so let me ask one more question and then you can just improvise the answer. After I ask this question, I will again take more response. Okay. Everybody knows how to walk? Everybody knows how to book IRCTC ticket? You can code how to book IRCTC ticket? Can you code how to walk? Can you code to make a robo walk on its own? Right? So, ultimately we are talking about tasks, things that we want to accomplish, which we know we can do, but which we do not know how we ourselves are doing. Okay? You know to walk, right? You know to ride a bicycle. Can you break it down? You cannot say that, oh, put your right leg forward, left leg forward, and then. Why is this? This kind of specification is not enough to program, right? Versus IRCTC, you could actually break it down into a set of if then else hard-coded statements, and then you can get the output that you require, right? The reason why you are not able to program is you know how to walk, but you really cannot break it down into any further atomic set of commands, right? You are riding a bicycle, you have learned, you have quote unquote, you have learned to ride a bicycle, but you cannot specify how you are riding a bicycle, right? So this is where, just from calculators to computers, you had this concept of programming. From computers to AI, see, ultimately when I break down everything, right? So you have a machine that is running ChatGPT, you have a calculator, you have a computer, all of this is fully only made of electronic components, right? If I just open it up, you are just going to look at silicon, right? That's all that you are going to look at, right? So where is the conceptual leap? The conceptual leap from calculator to computer is happening because you can program, right? And the answer I think somebody gave, right? The closest one is that when you are talking about artificial intelligence, what you are talking about is not just fixed if then else coding, but then you are talking about programs which can learn, right? What do you mean by which can learn? You yourselves do not know really how to hard code it, right? Because some of those tasks, the common tasks that we are doing, which is just to walk or to throw a ball, right? If I want to just drive, right? These are things that we really are not going. Actually, IRCTC, this is how we go, right? Oh, let us go here. So if you are going to go to a terminal, right? In the old days, if you actually have to manually book a ticket, that's what they would check. Oh, if this is free from here to here, then I can issue a ticket, right? So that is something that you can spell it out, automate it, code it, right? But you cannot actually spell out how you are even just throwing a ball, how you are even walking, or how am I even just picking this thing, right? These are not things that you can actually break it down to commands and then program it, which is where you need learning. Okay, so now what we will do is, we will look at the paradigm of what is known as rational agents, okay? And in this paradigm, what we will do is, first draw the paradigm, and then we will try to fit in all the keywords that we had, right? We have all the keywords here, and then we will try to fit in some of the keywords in the paradigm that we have, right? So basically, as I said, right? So once you want to engineer systems, when you want to engineer systems, you would want simple and sound principles that you can repeat, right? So if you are going to say that, oh, I have a dream and then I'm going to build an AI that's going to talk, it's going to have this intuition, somehow it knows, it can understand what I need, etc., etc. That's all just magic, right? That's all there in fiction. You can write a nice movie script, right? But if you want to really engineer, you need a solid framework and you should pin down the details of what you are going to talk about, right? So framework for AI is what is known as the rational agent framework. Right? And it goes by this very simple thing, which is there is an agent and on the other side you have the environment. Okay, environment is one of the keywords that all of you specified. Okay, so the environment has what is known as the environment has situations. Right, the environment presents the agent with situations. The environment situation keeps changing. Okay, so I am also going to draw a kind of a box so that you sort of understand. Right, these are two different entities. And what is the agent supposed to do? The agent observes the environment. Okay, so the agent observes what are known as features, right? Observations, or these are known as features. Okay, then based on that, the agent makes some decision, right? And then for learning to happen, what you have to do is you have to sort of provide the agent with some kind of feedback, which is a reward. Okay. Now almost all the tasks that we are solving can be put in this framework, right? So now what we will try to do is sort of take the standard popular tasks that AI is doing, and then try to bucket, right? And then we will also identify these keywords. Okay, so already one of the keywords, this keyword I have already put. Situation is a keyword that we have already ticked. Outcomes, actions, decisions, these are ticked. Environment is there. Context is what you observe, right? That's the feature. Context is ticked. This problem we will come to. Previous experience we will come to. Observing situation, this is done. Response is also done. This pattern recognition we will come to. Purpose is food, which is objective. This is basically reward. Okay. Again, environment. Trial and error we will come to. Long term, short term, yeah. Feedback. Feedback is something that we have done. Okay. So now what we will do is we will slowly take three important tasks. Okay. There are only three kinds of tasks, okay, that can possibly occur, fundamental kinds of task varieties, okay, which is descriptive, predictive, prescriptive. Okay. So suppose I give you some set of what is a descriptive? So how do you, within this framework of this rational agent framework, how do we differentiate these three tasks, right? Then slowly I am going to bring all the mathematical notation also, and slowly I am going to bring in the learning paradigms also, right? And we will also populate some of the other keywords. Okay, can somebody give me an example of a descriptive task? What would be a descriptive task? Okay, summarization. Okay. Reading something. Okay.
So categorization.
Categorization. Okay, under what categories?
Like anything like predicting if a given image is a cat or a
descriptive.
That's right.
Predictive. Okay. Give me a thing that is descriptive. Huh? Observing. Okay. Just observing. Okay, maybe back. And there, then.
Give a photo to someone and ask him to describe what is happening in the picture.
Okay. Huh? Details, okay. That's what is summarization.
Characterization.
Huh?
Characterization.
Summarization, okay.
Observation and conclusion. Observation, conclusion may come with the visualization.
Okay, visualization. Okay.
Sir, a regular attempt to identify in this job that which objects are purchased together. Something, it is a description that which objects were purchased together.
Okay, so let me get into some more specifics. Okay, for now we will stop these questions. Okay, so basically these are, so descriptive tasks are where, so you have the environment, okay, right, and then the environment throws some, the environment has some situation, then you are making some observations, right, the agent makes some observations, the agent observes. It just observes data, right, and it is just either summarizing the data, or it's just visualizing the data, it's just representing the data, right. Examples of these tasks are something like clustering, right. Say suppose I give you some set of data points, right, and then say okay, there is some bunch here, some bunch here, and then some bunch here. You just know that there are 3 groups of data, right? Or say I sort of give, so what I'm going to do is, I'm just going to add and then just going to something like you want to cluster things, right? Suppose I give you some set of newspaper articles and then you would want to segregate, saying that okay, some of this comes from politics, some of this comes from sports, and some of this is about cinema and so on and so forth. So just grouping data together and then just visualizing the data. You are not making any decisions on the data. This is just for the agent's internal representation, right? So you could also do something like, say somebody gave you data which is like this, right? You would want to kind of do some kind of dimensionality reduction, right? So you know that most of the data is in this direction, and less amount of data is in this direction, right? Most of the data spread is this side, and only less data is spread on the other side. So something like dimensionality reduction. So what the agent does is just it observes, takes the data, creates its own summarization of the data, visualizes the data, then just manipulates the data, does not convert it into decisions. Okay. So next comes what is known as the predictive tasks. Right. So this is what is known as descriptive, right? Then can you give an example of predictive task? Classification, such as what classification? You can just say image classification. Binary classification. Okay, or image or binary classification or any discrete number of classes, right? This is where the regression, okay? Right? Estimation, and what are you predicting? Estimation is you are estimating some quantity. What are you predicting? In order to predict, you have to estimate. Louder. Okay, that is prediction, right? You want to predict on new data.
Predicting the scores of different matches, like
okay, that's just regression, right? Okay. So here, what's happening here is somebody said something. I think. Analyzation. No. Differentiation. What? Sentiment analysis. That's. Where is the sound coming from? Oh, okay. That's still classification, right? You are classifying it into good sentiment, bad sentiment, right? So what here happens? Okay, fine. Let us just take image, right? So let us say image classification. Okay, now we would want to talk about things slightly more specific. Okay, suppose I am the agent and this is the environment. Okay, we are going to play this game, right? What is this? You are the agent, I am asking you to classify. What is this? Remote, okay. So what is the situation here? What is the situation? Okay, let us play this game some more so that you understand. So I want you to, in this exercise, I want you to tell what is the situation, what is the observation, and what is the decision, and what is the reward. Okay. What is this? Okay. So in all these things, what was the situation? No. Prediction is what you are doing. What is the situation? Observation is here, no? Wait. Observation is what you see. Situation is what the environment has. Okay. What is the situation? Okay. Can you be more specific? What is that you observe actually? Okay, what is the decision finally? Let us go from backwards. What was the decision here? Okay, what is the right decision? What is this? What is an example of a wrong decision? If I say this is a water bottle, right? So what is the decision here? Telling the category, correct? What is that you observe? In more precise terms, do you observe the object? What is that? What is there? So suppose I show this to a computer. What is that the computer is going to see? It's going to look at an image, right? It's going to look at pixels, right? So the observation is just the image, right? So in this situation, so what is the actual situation? The actual situation is the true category, right? When I show this to a computer, the computer has no idea that it is a remote, right? When I show this to a computer, the computer has no idea that this is a water bottle, correct? All that the computer sees, all that the AI will see is an image of this. So it's going to have a camera, and then in this camera, in its vision field, it's going to see pixel information, right? So if it is going to be a megapixel camera, then this is some vector in r to the power 10 power 6, right, into maybe 3 channels, right, RGB, right, and then each channel, it's going to have a million numbers for each channel, right, maybe 1000 cross 1000 dimensional, each row and column, it's going to have maybe 1000 coordinates here and 1000 coordinates there, and that's how you got megapixel, and that's the number. It's going to get just the raw number, and then that it has to predict, it has to classify correctly, right. So this decision equals to predict the true label. Okay, and who is having the true label? The environment has the true label. That is the situation. The situation is nothing but the okay. Now what is the reward? So suppose if you say that this is, if the prediction for this is remote, then you would say, oh, reward is 1. If it is going to say something else, you are going to say that the reward is 0. So the reward is basically if predicted label right, 0 if prediction is not equals true. Okay. Now what happens? We will go to prescriptive. Can you tell me an example of a prescriptive task? Recommending what? Why is that so? Because you are prescribing. Okay. Medical prescription. Okay, what happens after the prescription? Somebody recommends a medicine, then after that, what happens? Huh? What is different from, what do you think differentiates prediction from prescription? Okay, in the medical scenario, can you differentiate prediction and prescription?
Prediction is based on the prediction is totally based, like not the confirmation. Like prediction is that maybe today Mumbai Indians will score 200, 100. But the prescription is that for getting into final, you have to get the perfect score or the minimum this score to go there, or you have to win this message, like 3 matches, 4 matches to clear the final round. That's the prescription. Prescription means exact conclusion, like it's not random, but the prediction is like random. It can be yes or no. But the system is totally yes. You have to be like that. Like the system of the paracetamol is for the fever or this that. Not like anything. You have a stomach pain or you have anybody anything pain in the body and you will go for paracetamol. That's the prescription.
In this framework, you have to differentiate. Anyway, okay. Some other answers.
The action of probability could be considered under prescription because on the base of probability only we prescribe something like
the doctor just tosses a coin, prescribes. Okay, 1 crocin, 1 dose is 50.
on the basis of again the point we explained is
Okay, let me specifically ask a question. In the context of medicine, right? What is a prediction and what is a prescription? Huh? What is prescription?
so prediction is something where we
Okay. So, okay, here is an answer. Prediction is the disease, saying that you have a disease. Okay, so suppose I say that, looking at the lung, X-ray, chest X-ray, I say that, oh, you are going to have, you are having tuberculosis at this level, your lifetime is maybe 6 months left, right? That is just prediction, right? You are predicting the lifetime of the patient. Looking at the features, which is basically the image, right? Chest X-ray image. But prescription is take this medicine so that the situation changes. Okay? Ultimately, when you are doing a prescriptive action, the decision is going to influence the situation. Okay? In any of the prescriptive tasks, you are actually influencing the environment, right? Do this and then the situation is going to improve. So can you give me another example? Very straightforward example of prescription.
Sir, I have a different question. Minutes before you asked the question that we really need a brain to think. Sir, but you didn't answer.
I answered, right? Huh? Yeah.
You didn't answer that question, sir.
I answered. I said, if you are going to talk about intelligence, right, we really don't have to ask the question of does the computer really have a brain or not. All that we have to understand is how decisions are being made. So understanding or building engineering artificial intelligence is more about understanding how decision making is, how do you come about, how you arrive at decisions rather than a question about whether we can rebuild the brain or not. Right? Okay. So playing chess, that's another example of a prescriptive task, right? Where you actually get to observe the situation fully. You actually see, you don't have to, otherwise you are playing something like a blindfold chess, you can actually observe the board fully, right? You know the situation, right? And then your action is to change the situation, right? That's where the prescriptive task comes. Okay? So now, prescriptive task is where, right? Here you actually don't, actually this does not, so you only predict, okay? And then you do not influence the environment. In the prescriptive task, the agent actually influences the situation. And then you decide and then you get a reward. Okay. So these are the, what happened? Yeah. So as you can see, here in the descriptive task, the agent does not really make any decision with respect to the environment. Right? It is just making some internal representation. That's it. It doesn't really care. It's just summarizing for my own sake, which does not get converted into a decision per se. And in the predictive task, you are actually not sort of influencing the environment, right? So I can predict, oh, tomorrow it's going to rain, right? Or tomorrow it's not going to rain. Then that's not going to change the way the environment behaves, right? Any of my actions, my decision is to predict what's going to happen, what the situation is going to be. Right? I am predicting the situation, I am not really influencing the situation. When I am prescribing, my prescription is to improve or change the situation, take control, okay? So this is basically to take control of the environment, such as self-driving cars, right? So you want to control the environment, okay? So these are the three kinds of tasks. Now what we will do is, we will put these three tasks to the three methods, right? So whenever you are doing descriptive task, it is known as unsupervised learning. Okay, where you are given data, right? You are given just bunch of data, some observations, we will call it as x, right? xi equals 1 to n. These are in some d dimensions, right? Basically all that I am saying is that, okay, here is a bunch of measurements, that's all. You might want to plot it, visualize it, compress it, right? Cluster it, see, oh, okay, these many kinds of groups are there, right? You are not converting it into any decision, right? When it comes to predictive task, you get what is known as supervised learning. Right, where you are given the observations and also the true labels. You are given xi, yi. Right? You are told for this observation, this is the true situation. Right? You are told that, oh, this category is that of a remote control and this is how a remote control looks. This category is that of a dog and this is how a dog looks. This category is that of a house and this is how the house looks. Right? So where you are given labels, right? Where you are actually given what is the true situation and then you are also given observation. Right? This gives you the paradigm of supervised learning. Basically supervised learning is to solve predictive tasks. Right? Or you just say that, oh, this is the customer data, customer's age is this much, customer salary is this much, customer has a house, this is the credit history of the customer. Then you would want to predict whether or not loan will be paid or repaid. And you will have data, past data of all the customer attributes, the features, and then you will also have the label which said loan paid or not paid. Right? So in predictive paradigm or in predictive tasks, the solution method is basically supervised learning, right? Where you are given observation as well as the true label. And when you want to prescribe things, you are in the paradigm of reinforcement learning. Okay. So where you have to give lot of information, right? You have to say, okay, the situation was X, right? And you can sometimes observe the situation fully X. If you are looking at the chessboard, you get to observe the chessboard fully. You don't have to predict the chessboard. You actually have full observation, right? If you are driving the car, you can actually see what's ahead of you. You are not closing and driving. You don't have to predict. You don't have to guess. Whether this vehicle is there or vehicle is in front of me or behind me. I actually know, right? I can fully see what vehicle is there. But then I still have to steer. I still have to press the brake or the accelerator, right? So that I can change the situation, which is the position of my vehicle with respect to other vehicles, right? And then you make an action AT. Then based on the action, this goes to xt plus 1, right? The state changes, the situation changes based on the action that you make, and then you get a reward, right? So typically in reinforcement learning, the data is always what was the state, then what action did you make, then what happened next, and then how much reward did you see. And this will be the data set, right? T equals sum 0 to n. This will be your experience, right? So the place where data is coming, so basically all that you are doing is you are working on this data, right? This is the data that all the while we are saying experience, previous experience, data, right? Using learning from this, this is the data that we are talking about. As you can see, the data gets more and more sophisticated, right? In descriptive, you just need the observations, that's it. You can just group it and so on and so forth, right? You don't even have to predict anything. When you want to predict, you just have to predict, you just have the true labels, end of story, right? When you want to really control or prescribe, when you want to really take control of the situation, you have to remember what did you see, what did you do, and what happened next because of what you did, and then how much reward you got. Okay. So now, what are the challenges of reinforcement learning? Okay. Now, as you can see that this is a prescriptive task, right? You really have to learn by trial and error. Right? So this previous experience, right? This is all from data, right? So there is this learning by a failure and trial and error, which is what happens in reinforcement learning. Okay. So, and there is also this concept of where is this? This long-term goal. So we will now look at these two aspects. Okay. How do you learn from trial and error? How do you balance? And then how does this long-term goals, right? How does it affect us? Okay. So let me ask a very simple problem. Okay. Let us take a very simple environment which is known as grid world. Okay. So in this environment, suppose think that, so this is like some maze. Okay. In this maze there is a mice, okay, sitting here, right? So there is maybe cheese worth of 1 here, cheese worth of 10 here, okay, and this is all. If you visit this place, you always can get cheese worth of 1 every round. Every time you will keep getting, there is some source of cheese, right? It eats, then it gets replenished, but it gets replenished only by only 1 amount. If it goes here, it can get 10, right? Or you can think that this is like the quality of cheese. And it can go up, it can go left, right, left, or down, or it can actually stay. Okay. Suppose I am going to say that only t equals 1 step remains. There is only 1 step. T equals 1 is the time left. Okay. So what do you think that the mice should do? You will just go right, correct? You will just go right. T equals 2. There are 2 steps left. Go right and stay. T equals 3. Same. T equals 4. Go to. It can go only, right? Here it's also going to be the same decision until t equals 5. Right? T equals 5, what can it do? No, 5, it will still require more than 5, right? 1, 2, 3, 4, 5, 6, right? Until t equals 6, the point is that it has to go, just go right and then stay there. But after t equals 6, what happens? It can actually go like this, right? Or I should just say, so now, intermediate, right? When you are actually going, the mouse is actually starting, right? Here it gets nothing, here it gets nothing, here it gets nothing, nothing, nothing. Only then it gets 10. Okay? So, you have to balance what is known as the immediate reward and the future reward. Okay? That is what somebody responded by saying, you have to look at the long-term objective. It's not like, okay, now I am getting a reward of 1 and I will do it, right? So you have to balance the immediate reward and the future reward. Okay. So when you are looking at reinforcement learning, the first aspect is immediate versus future. I mean, this is very, very different from a supervised paradigm, right? Because I am asking you what is this? This is a remote, that's it. Either told it correctly, incorrectly, that's it, over. Then I am going to ask what is this? You will say, okay, it's an iPen, right? That's it, over, right? There is nothing like, all that you care about, the immediate reward, immediate answer. This you have to get it correct, right? there is no balance. So somebody is asking, oh, whether it's going to rain today, tomorrow or not. You have to tell tomorrow the answer will be known, whether your prediction was right or wrong. That's it, right? There is nothing like this long-term consequence of your today's action affecting something in the future. There is also another issue. So suppose I play chess, okay, and I made some move and then finally I won. Can you tell which was the move that gave me the victory? No, right? You really cannot tell which is the move that actually gave me the victory. Okay? It is the entire trajectory that is giving the victory, right? So there is what is known as temporal credit assignment. You really cannot pin down, this is the action in this place, that is why I actually won. Maybe you will do a queen sacrifice. The immediate consequences, you lost a piece, but then 20 steps later you would have won the game. So every time do you go and do queen sacrifice and then you are guaranteed 20 steps later you will win the game? No, right? So it is this connected set of actions, right? And then you really cannot pin down this particular decision of mine at this point of time is the one that cost me the victory, right? Or gave me the right reward, right? So this is again a very unique, challenge or unique aspect of this prescriptive problems are this reinforcement learning, where you apply reinforcement learning algorithms, right? You really do not know which action cost what, right? All that you can see is that if I do this, I get this reward. If I do something else, I got some other reward, right? So this is the temporal credit assignment problem, right? So then the third part is what is known as the exploration versus exploitation problem. Okay. Suppose I have to say, suppose think of the case where you have to place advertisements, right? So Google ad placement. Okay. So let us take this example. So there is a website, okay, and then you can place ads, right? This is one position. Maybe you can place an ad here. Maybe you can place an ad here. There are 3 locations where you can place an ad, right? This is 1, 2 and 3. Which one would you, where will you choose? Huh? Why? Third, why?
Because after the scrolling the tab, one will be go outside, and this, the last one, second one will be the programmatic for the recent coming scroll or page. But the third one will be even and managed one, because it will be like unresourcing for our views, our view to observe it like this.
Now.
Now that is the exploitation. That is exploitation. We can't do with this. We can't bear with this.
No. So the point is that unless otherwise you place the ad, unless otherwise you get the feedback, you will really not know.
Yeah, that's it.
Right? You have to have people coming and clicking, and then only after they click, you will even know. Right?
Feedback loop.
You need the feedback. Only when they click, you will be able to figure out whether they really click. Okay. So now suppose I go and keep the ad today. Okay. So I kept here. Maybe here there are 20 clicks, right? And then today's data, right? This is 20 clicks here, and then maybe the next one was 30 clicks. Then this is 15 clicks. Okay, this is one day I have done this, right? So then what will you do? Can you always say 2 is best?
No, no.
Why?
Because we have to also mention the web page which is the user visiting. Because we can't only focus on the ad. Ad is only the main content when the web page is the visible or user coming and going back and giving the reviews or getting the good experiences. If the user doesn't give the good experiences, then there is no need to be ad anywhere. So whether it will be on the web page or on the side of the content.
Okay, so the user experience will keep changing.
Yeah.
Okay.
Feedback. With the feedback we can change this.
So this is today, okay? This is today's experience, okay? T equals 0, right? So tomorrow same thing, same ad I keep here, maybe here this is 30, this is 15, this is 40, right? So the issue is that even when you are actually having these options, right, there is inherent randomness in the system, right? So you will really not be able to measure in finite number of samples exactly which is the best option, right? What you have to do is you have to exploit the data, which is basically you have to make use of the data that you already have, but at the same time you should also explore, right? So what I will do is I will keep track of the historical data, right? And then every time I will do what is known as something like an epsilon greedy strategy. Right, where what I do is I have historical data, okay, play the action or what do you say, choose the option, right, that is historically the best with probability 1 minus epsilon. Right, but with probability epsilon, choose a random option. Right. So what I can do is I have this historical data, right? So according to this, I know that this is giving 50, this is giving 45 and this is giving 55. So option 3 is better, right? So I will just go with option 3. So every time if I go with option 3, then I will have no information on 2 and 1, right? Every now and then what you have to do, you have to give some chance to 2 and you have to give some chance to 1. And how would you do it? Only if you give a chance to 2, maybe you would have done this, right? So this is what it is, right? You gave, and then like this, right? Then maybe had you are just doing this, right? So this is 55, so you thought that okay, I will only give 3. So next day it was 20, it was maybe 50, right? So 15 maybe. Then suddenly you say that, oh, one day I will give chance to 2, right? See here the data is missing, right? Because I didn't give any chance. And somehow just by this randomness I introduced inside the system, I kind of, the way I am choosing, one day I gave chance to 2 and then I see that, oh, this is somehow 70. Then all the while I am thinking, oh, I was thinking 3 is best, but then somehow 2 is best, because these 2 days when I observed, I was observing bad samples, right? It was just bad day for 2, right? And then actually it is as good as 70, right? Then what I will do is I will give more option to 2 now, right? But then every now and then I will have to go and explore the other options, because 1 didn't get a chance, right? Otherwise 3 didn't get a chance. So what you have to do is, because your signal is only reward, right? It is unlike supervised learning where you are told, if you are given a data set, you are given a bunch of images of cars and then you are said it's car. These all look like cars. These all images look like, these are all images of cats. These are all images of dogs, right? These are all images of horses. That's how the data set is, right? But then in the case of reinforcement learning, the only thing that you get is the reward, right? I gave this medicine, this patient got cured. 80%. Same medicine I prescribed to somebody, then the person got cured only 20%, right? So there is variation in the effect that your prescription, that your action is having on the situation, right? So what you have to do, the only signal that you have is reward, and then you have to keep measuring the rewards for the various options again and again, right? Every time you have to balance the exploration, which is basically you have to exploit what you already know, exploit prior knowledge, but at the same time explore options. Right? So all of this reinforcement learning deals with what is known as this explore and exploit problem. Right? That's a very, very core aspect of reinforcement learning, because you are only learning from rewards. You really don't have what is called as the right answer. You only have rewards. Right? So you have to keep mixing things up. Right? And how do you do it in a principled way? Right? That is something that you would anyway learn in the course, but that is a very cornerstone of that's a very key aspect of reinforcement learning. Okay. So then there is what is known as lack of model information, right? So you don't have, okay, say the same grid world, okay. Okay. Same grid world, suppose the mice did not know, right, that reward 1 is here, reward 10 is there, maybe there is some danger here, say something like a reward of minus infinity here, maybe somebody has put a poison somewhere, right. If you go to these places, you will, maybe the mice, somebody has poisoned and then it is going to die. Suppose it does not know this, right, how is it going to learn? Right? It has to learn via experience and repeated samples and trial and error, right? While it will, so this explore and exploit, it will tell, okay, maybe it knows that, okay, it has learned that, okay, this is a safe route, right? But every now and then what it will do is, it will kind of say that, oh, maybe if I go here, maybe there is something here, right? So that it has to do trial and error, right? But at the same time what it has to do is what is known as incremental learning. Right? So it cannot, it will go and then it will incremental learning, meaning it will via some kind of step size based update. So what do I mean by that? So what it will do is, so initially it will have no idea, right? Initially it will just think that, oh, everywhere it's only getting 0, right? So everywhere you just think that it's getting 0. It does not know anything, right? Everywhere it will know that, oh, I am getting 0. But then once it goes, right, say maybe it goes this, it say maybe it transition from here to here, okay, and then it will receive a reward of 10, right. So what it will say is that, oh, okay, the value of this place is not 0, right, but it is 0 plus some small increment, let us say gamma times 10, right? So maybe you can put a value 0.1. Right. What it will say is that, oh, you will go and say it will update information at, say, at t, this is the information, at t plus 1, you just make a small update. So it will say, okay, this is not 0, but this is 1. Okay, right? But then this is not really 10, right? It has to visit it multiple times. Every time it will say, oh, my value I thought it is 1. So next time it will, so this will be here, right? Then maybe it will go so and so on and so forth, wherever it is. Then maybe sometimes it will make this transition, right? Then what it will learn is, oh, here I was thinking it is 0, but actually I am getting a reward of 1. So what I will do is I will say this place is not 0, but 0 plus 0.1 into 1. So it will say this place is 0.1. Right? But this is still not the true value, right? So what we will do is we keep on visiting these places, it will keep exploring, right? Every time it will try to go to the place where it is having more reward, but at the same time it will also keep updating. But next time it goes and visits here, right? It will say that, oh, my value is 1, but then the actual value is 10. So the amount I have to correct is 0.1, 10 minus 1, which is 1 plus 0.1 into 9. So I will say, oh, this value is not 1, I will just update it to 1.9. Right? So after it does this incremental updates, it will actually learn the true values, right? As it keeps visiting, as it's doing trial and error, it will have these true values, and then at any point of time in any state what it has to do is, so it will have these values, right? So it can compare the values in each of the actions, right? Just as we saw in the video, right, where the cyclist is kind of comparing, right? Basically what he is comparing is the values that the cyclist will get in each of the options, right? So after learning everything, maybe this was value worth 5, this is maybe value worth 6, this is value worth 3, this is value worth 2, then we will say, okay, taking the action that gives a value of 6 is going to be more useful than going in any other way, right? And this happens via incremental step size based updates. Okay. So this is also something that you will learn under the name of temporal difference learning, right? I am not giving any keywords because you anyway have the full course, right? So the aim of this session was to tell you, convey you the basic ideas without, taking support of mathematics. Okay. So one last part that is there that comes up in reinforcement learning algorithms is what is known as curse of dimensionality. Okay. Suppose I have a junction, right? In each lane there could be 0 to 9 vehicles. 0 to 9 vehicles can be in each lane. How many possible configurations is this traffic junction? Each lane can be 0 to 9. This lane also can be 0 to 9. This lane also can be 0 to 9. How many? 10 power 4. Okay. Suppose I add another junction, what happens? Now put together, say if I have only 2 junctions in my entire city, what happens? Now how many possible combinations? 10 power 8, right? This is 10 power 4 into 10 power 4, right? If I put 2 identical things, the problem does not become twice as hard, but it becomes 10 power 4 times as hard, right? The size of the combinations that you are supposed to look at, right, simply blows up very fast. For example, the Go game, right, for which they designed the reinforcement learning algorithm, which is known as AlphaGo, the number of board positions is greater than the number of atoms in the universe. Okay. So, the size of the state space can, yeah. Okay, we will come there. So, there is this what is known as the curse of dimensionality, which means each and every state you will really not be able to find out what is the right action, which is where you have to do what is known as this pattern recognition, right. So, you have to find the commonality between states. You should have a way to react to the situations based on the similarity of the situations. You cannot really learn separate kind of values for each and every state, but you have to understand the pattern between the states and then across the states, and then you have to somehow compress all the information and then do the learning, and which is where you will have this deep learning and representation learning come into picture, right. So, you give the data, you give the observation, you give the features, and then the deep network, right, learns the right representation, right, extracts the right kind of pattern from the situation, so that you really don't have to store these values, right. So, you can imagine, right, this is a grid world. In this grid world, right, you need for you to know to make decision each cell, you have to do 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, right, 15 values you need to get directions. You cannot really store, if there are 100 junctions, you cannot just store 10 to the power 4 into 10 to the power 4 like that 100 times, you really cannot store all those values. So, what you want to do is you will take that information, that feature, you throw it into a deep neural network, right, and then the neural network kind of extracts the right information, right, and all that you end up learning is the weights of the neural network, which is much lesser than the number of situations, right. You do not really learn all the possible board combinations, what should be the move, right. You just train a deep model, the deep model kind of learns the right representation, right way to extract and summarize the information, so that it can be later converted into decision. Okay. So, yeah, maybe one question and yeah. Oh. Last page here. Ah. These are just two different junctions, let us say. I am saying if there is one junction, there are 10 power 4 configurations, right? No, I am asking a question. If there are two junctions, how many number of states are there? Related to what? Huh? Relate what? There are no two junctions. You have never seen two junctions. One junction is here and one junction is there. Why? There are two, one junction in one city, another junction in another city. Why should they be related? One junction in this area, in Adayar, maybe one junction near Tambaram.
Yes, sir.
Why should I not consider both? It's an example. Okay, I am asking a question. Consider Kumar is having 5 pens, Raju is having 6 pens. You are asking what is the relationship between Raju and Kumar. Why do I consider Raju and Kumar? Maybe they are brothers, maybe they are friends, maybe Raju was dead. We don't know. It's an example. It's an example. Okay, there is no relationship between this junction heads this junction. Okay. Huh? Yeah, what is the doubt? Huh? Why are we considering two junctions?
Yes.
Just like the way I considered one Kumar and one Raju. There is no relation. This is the total count, na? Total count of the possible number of configurations the entire thing can be, right? Okay. Yeah. So, yeah, maybe one more question and then I will kind of summarize, then we can have more questions.
So the two junctions, they are different from each other, they are not connected. So won't the number of dimensions be 2 into 10 to the power 4?
That is why I am asking, is it 2 into 10 power 4? It is not.
But they are not related, they are in two different parts of the city, there is no connection between them. So why will it be 10 to the power 4 into 10 to the power 4? That would happen if they were both interconnected.
Is it? If it is not interconnected, it will not happen?
But they are two separate problems.
Yeah, these are two separate links. Why did we get 10 power 4 in the first place? 10 into 10 into 10 into 10. Why is it not 4 into 10?
Because all the 4 junctions there are interconnected with each other in the first case and again separately in the second case.
If I write all these things, okay, so this is x1, this is x2, this is x3, x4, x5, x6, x7, x8, x equals x1 to number of possible ways of filling this.
But sir, x1 and x4 are connected, but x1 and x6 are not connected.
Let it not be connected. You are saying 5 vehicles will stand here and then 3 vehicles cannot stand here.
But they are not, but they are separate problems.
They are not. These are two signals I am saying. Suppose I think of a scenario. There are two signals, definitely some junctions. You can imagine 2 junctions in Chennai. I am saying how many vehicles are standing here, how many vehicles are standing here. Okay, I can have 5. I can have 10 pens in my pocket. Okay, you can have 10 pens in your pocket. What are the possible configurations? Maximum of 10. What are the various possible configurations?
It could be anything, 1 to 10, so 10 square.
Same thing. That's okay. So again, we are kind of close to time, right? So what I want to sort of say is that, right? So when we are talking about AI, we are talking about engineering systems. Okay, we are not really talking about whether AI is having a brain, whether it is having a feeling, etc., etc. If you really want to engineer systems, you need a formalism. The formalism is that of this rational agent framework, where you say that there is a situation, environment presents a situation, you are observing and then you are deciding. And in this framework, there are basically 3 kinds of tasks. One is descriptive task, right, where you are going to propose solution. Descriptive task is the problem and the solution to the problem is unsupervised learning, where you are just summarizing the data, visualizing the data, you are just doing dimensionality reduction, right? Or you are predicting, which is like either classification or regression, right? In which case you are predicting about the true label, and then you have labels when you train. And then the third possible situation is what is known as prescriptive, right, which is the set of algorithms that is there for prescriptive task is what are known as the reinforcement learning algorithms, where the actions that you make actually change the situation. They can change the environment. And in this framework, the most 3 important things are that, the most critical thing is that you learn only via rewards. Because you are learning only via rewards, you have this aspect of you have to balance the immediate and the future rewards. You really do not know, which action costs which reward. You really don't have this temporal credit assignment. You really cannot say that, oh, this particular move was the one that actually led to the victory. It's a combination of your actions that leads to the rewards. And you have this exploration exploitation, right? Because there is randomness in the system, you have to go and explore the options, even though historical data will suggest that they are bad options. Every now and then you have to give chance to second best or the third best option, just to learn more about those options, right? So these are 3 things about just learning from rewards. And then because you don't have explicit model, you are directly interacting with the environment, you will also have these algorithms where you will make incremental updates, right? And then as and when you observe a reward, you just maintain an update for what happened, right? And then since you don't have this, since you have this cursive dimensionality where the number of possible combinations is much larger, you really cannot learn separate values for separate situations. You somehow have to have a very compressed way of representing. So, which is where deep neural networks are helping us, right? And then that's where you have representation learning. You learn the right representation, you give in the board position, or you given this configuration of the traffic to a neural network. The neural network just has to learn the neural network weights. You don't have to learn separate values for all this. If there are 100 junctions, then you can clearly see that it's going to blow up very fast, right? You don't have to learn separate values for each of these configurations. You just can give in the vector, and then the neural network can throw out the right decision, right? So that's what is known as deep reinforcement learning, right? Again, to summarize, AI is giving you set of tasks, and machine learning is basically giving you methods which are based on data, and then depending on the tasks, the methods also vary. If it is a descriptive task, the machine learning method is unsupervised learning. If it is a predictive task, the method is supervised learning. If it is a prescriptive or a control task, the method is known as reinforcement learning. And reinforcement learning has all these challenges, which is what you would learn in the full course. Okay, with this let us stop, and then maybe we can take some further questions. Okay. Okay. So the question is, in incremental learning, why are we not immediately updating, right? So again, there could be noise, right? This 10 is what you observed, right? But then there could be some randomness in the 10 also. You really don't want to immediately say that it is 10. You say that, okay, it's more or less. Next time again I will come, then I will again adjust, right? So you really don't want to fully commit. You want to slowly learn, and then you want to slowly commit. Yeah. That's why you do incremental learning, right? So that you are just guarding yourselves against like high fluctuations. See, it's just simple, right? Says you have a friend, very bad behavior, suddenly one day the friend's behavior was good. You don't immediately change your estimate of how good your friend is, right? So okay, maybe today, maybe the mood was better, let me see. And then if the friend continues to be better, then every time you increment it a bit more, and then now then after a month's period you actually really think that, yeah, this person has really changed for the better, right? That's how we do incremental learning. That's why, I mean, that's the reason why we do incremental learning in life, also in algorithms. It is to take the variance in account, throw away the variance, and to learn the average behavior, we do incremental learning. First time it might be 10, next time it might be 5. Every time you increment, your increment is going to be based on the difference between your estimate and the actual reward, right? Okay. Any more questions?
So in the grid ball example, so I think the best solution is for it to first go to the grid with one point of trees and then go up to 10.
Yeah.
So then my question is, I think there's a certain amount of risk associated with this, like it could be risky at 1. Or we could go to 10, but that could also mean that there might not be any stuff.
Yeah, so that is what, right? So this is one instance. I can make up another example, right, where the rewards are totally different, right? Ultimately, what we are trying to say is that learning will happen via trial and error, right? You will try many such trajectories, and then you will keep going to the trajectory where you know that there is reward, but every now and then you will explore other trajectories, right? Sometimes when you explore, you might also end up in very bad states. That's also possible. Right? And then there is a separate area which is known as safe reinforcement learning, where how do you put these safety measures so that you don't go to states that are really bad, right? Yeah.
So can AI models learn to set rewards by themselves?
So rewards in general are coming from, okay, so if you set rewards on your own, right, I can set reward to be one for everywhere, right. So there is a balance, right, where say for example you are learning chess, right, the actual reward is just winning or losing, right, but that is what is known as a sparse reward, right. So there is this entire area of reinforcement learning which is sub area which is known as reward shaping, where you can sort of design slightly intermediate rewards, right, coming up with intermediate rewards, and then you sort of give it a clue, right, so that you know roughly these are the sub goals, right. So sub goals can give you better rewards, right. So that in itself is a research within the field, right.
Sir, what kind of reward an AI could give it to itself other than points?
What kind of
reward an AI could give it to itself?
Finally, we are talking about a number, right? This is about number crunching, right? These are all numbers, right? When you say observation, this is some number. This is a number, right? It is that's where we are. I mean, there is nothing else that is there. We have to calculate numbers, right? When we say reward, it could give itself meaning what? What else are you thinking in your mind? Are you thinking it will get some extra battery or something?
Like for us, and there are various various ways we can reward ourselves.
Exactly. That's what I'm saying. So we should totally take away all this. You know, AI is like a human. It has feeling. It has emotion. It rewards itself. It will not give. It will not become any happy because it got some extra petrol or it got some extra hard disk. It got some. See, it's ultimately this is all that we are committing to, and this is all that we will engineer. All these are just numbers. You calculate these numbers, you update, and you get your decision. That's all. AI is not a person, right? It might be cool to talk about it in very anthropomorphic, right? Yeah, that's the right word. Terms, right? But that's not what it is, right? So, yeah. That is exactly why I also said this brain is not required, right? Ultimately, you want to get decisions, you want to write algorithms, you want to write programs, right? Yeah. Yeah, okay. So if there are no more questions, I think I should thank all of you for your patient listening for this in this afternoon. Yeah, thanks. And I also thank all the volunteers so that they ensured all of this is in place.